In this video, we're going to do an introduction to differential equations. This is geared for a Calculus 2 course and is based on the OpenStax textbook on Calculus, Volume 2, Section 4.1, an Introduction to Differential Equations. This video is not going to provide a complete and thorough overview of differential equations such as you would receive in a differential equations course, but it will provide a basic background of what a differential equation is, what a solution to a differential equation looks like, and cover some basic techniques of how to solve one. Let's take a look first at what exactly a differential equation is. Since calculus is basically the study of change and of rates of change based on the derivative concept and the limit concept, then calculus is really an excellent place to study anything that is changing over time, whether this is the spread of a disease such as COVID-19 or the cooling of a body after death on the onset of rigor mortis, or if you're talking about how quickly a leak is draining a tank or a pool. Anything that changes over time is outstanding for any kind of calculus and differential equations application. There are other things that you can study as well, of course. You can study springs and weights and all kinds of situations apply. When you're looking at the spread of a population, whether you're trying to manage deer in the wild or wolves in Montana, you can study all of these using calculus and differential equations. So what is a differential equation? Since it has the word differential in it, you know it has to do with derivatives, and of course it does. A differential equation is basically an equation that has an unknown function, y, equal to f of x. This is the first time that you're not actually told what the function that you're after is when you start. You do, however, know something about the derivatives of the function. You may also know some value, such as the initial population or the number of bacteria originally present, or in the case of a body, you know what their temperature was roughly at the time of death. Then you can take the equation where you don't know actually the equation y, but you know something about the rate of change related to it and maybe an initial value. And you can solve that equation to find the equation y equal to the f of x that will satisfy that differential equation. Now, in a differential equations course, there will be a lot of emphasis put on what's called the interval of validity. Now, the interval of validity or the interval of definition or the domain of the solution is the interval on the real number line over which that solution will work. So in a differential equations course, that interval of validity is extremely important. We will not emphasize that in this course, but we will touch on it briefly here and there. Let me show you what an example of a differential equation is. This equation here that you see is an example of a differential equation. This is 2y double prime minus 3y prime plus 5y equals 0. You don't know what the function y equal to f of x is. You know that the function y is a function of x, where x is the independent variable. You just don't know what it is. You need to find an equation that will satisfy this differential equation. And you'll notice that we often use DE to abbreviate differential equation. So an equation y of x will be a solution provided that it satisfies that differential equation, again, over some interval. While we won't emphasize the interval here, it is tremendously important and you will need to think about it quite a bit in a differential equations class. Now, a solution to a differential equation is not going to be unique, generally speaking, because, of course, the derivative of a constant is 0. And because in the differential equation itself, you are dealing with different orders of the derivative of the function, which means any constant that might have been there has probably disappeared. So what you end up with instead are families of solutions up to the constant plus c. Now, this is something you're very familiar with. This comes out of the indefinite integral. You get the same thing. You get a series of curves that are solutions to the indefinite integral up to the constant plus c. Now, I do want to make one other definition, which is what's called a singular solution. A singular solution is one that does not actually depend on the independent variable at all, and it may not have the form of the general solution that you might find that for equations that will satisfy this. In other words, it may not be a member of that family of solutions that will satisfy the differential equation. Usually they're not. However, they do solve it. Now, let me give you an example. The trivial solution, y equals 0, is one example. So if we're looking at this right here, and I were saying, okay, well, let's just do the x-axis, right? Y equals 0. What could be simpler? Well, if y equals 0, then 5 times 0 is 0. Okay, well, what's the derivative of 0? 0. And the second derivative of 0? 0. So you do get a true equation, 0 equals 0, but it will not be of the same form as most of the family of solutions that will solve this differential equation. We call this a singular solution. You generally have to look for those separately and with different techniques than looking for the family of solutions. Now, we call it the trivial solution, not because it's necessarily easy, but because it is true without a great deal of work. So in the case of trivial in the mathematics class, realize that trivial to a mathematician does not mean the same thing as it does to an English professor. Trivial in mathematics means, okay, this is a weird exceptional case, and it's true, but it doesn't follow the normal pattern. That's what we mean by trivial. Not necessarily easy, just not in the normal pattern, and true without a lot of work, and not following the normal pattern. Okay? Most of the time, what we're going to be looking for are the general solutions and not the singular ones. Let's take a look at our first example. We want to show that this equation here is a solution to this differential equation on the interval where x is greater than 0. So in order to do that, what we need to do is we need to substitute this equation in place of y in the differential equation, find its first derivative and substitute it here for the first derivative, then find its second derivative and substitute it here for the second derivative. Then we want to combine all of the terms and show that this does in fact lead to 0. In other words, to prove that it's a solution, everything must take place on one side of the equation without moving things to the opposite side. You're trying to prove that this side does equal 0. Go ahead and pause the video here, compute the first and second derivatives of y, substitute them into the differential equation, and see if you can prove that it is. Then turn the video back on and you can check your answer against mine. When you compute the first derivative, you should get -3/2 x to the -5/2. You can drop the x to the 5/2 to the denominator where the sign will become positive. However, it's easier to take the second derivative in this form here. That allows you to bring the -5/2 to the front, reduce the power again by 1, which of course you could rewrite in this format if you wanted to. Then you take each of these pieces and plug them in place of y prime and y double prime in the original differential equation. Once you do that, you will need to use the properties for exponents. Remember that it is numerator power minus denominator power, or 2 minus 7/2. Since 2 can be written as 4/2, that's 4/2 minus 7/2, and that will lead to -3/2. Here you can rewrite the first power as 2/2, and 2/2 minus 5/2 is also -3/2. I went ahead and wrote the third one back in its power form in the numerator because it's easier since these are in that format. Notice that I can combine like terms. I could have added them all together here, but I went ahead and did it in two pieces. And again, you do then prove that 0 equals 0. Now, why did they have the restriction that x has to be strictly positive? Two reasons. First, we'll deal with y not 0, and then we'll deal with y not negative. Why not 0? Because up here, because of the negative exponent, you can see that you definitely have the variable in the denominator, and thou shalt not divide by 0. Therefore, x cannot be 0. Why not the negative? Because when you have a fractional exponent, a rational exponent, the denominator of that exponent represents a root or a radical. And since the denominator here is 2, that's a square root. And if you put a negative under a square root, you do get a number. It's just not real, it's imaginary. And since we're looking for real solutions, we've restricted it to greater than 0 only. Let's look at another example. Let's take a look at this one and show that this is a solution to this differential equation, again over the interval of validity, or the interval of definition, or the domain of the solution, whichever term you choose to use for where that solution will work. Go ahead and pause the video, compute the first and second derivatives, and substitute them into the differential equation in place of y prime and y double prime. Then restart the video to check your answer with mine. Let's see how you did with your results. In this case, when you compute y prime, it's better probably to leave it in the power form with the rational exponent written in the numerator. That will make it easier to do the reduction and the combination of different factors of x later on. When you compute the second derivative, be careful with the signs and make sure you get the right powers on the variable x. When you plug it into the equation, note that our interval of validity, or the domain of the solution, is again x greater than 0. Because we have a negative 1/2 power as a rational exponent on the variable x, this is the reason for the restriction x greater than 0. The negative puts it in the denominator, so thou shalt not divide by 0, and the 1/2 power is the square root. When we plug it into the equation, after some careful reduction, you do finally come to the result that in fact 0 does equal 0. You may want to pause the video in order to be sure that your answer matches mine, but you will receive the same solution in the end. Let's take a look at another example. In example 3, we want to show the trivial solution also solves that equation. Again, the trivial solution here does not mean simple, but it does mean unusual and not following the same form as most of the general solutions. In fact, if you plug this in, you know, of course, that the first derivative of any constant function is 0. In fact, any derivative of any constant function is always going to be 0. When you replace these into the equation, you get 4x squared times 0 plus 12x times 0 plus 3 times, yes, the equation itself is 0, and of course, it does, in fact, equal 0. In this case, they had a restriction x greater than 0, but this restriction is coming from the first solution that we found and not this one. In fact, for this particular equation, the solution y equals 0 would work over any interval at all, since this equation does not imply that y is ever in the denominator, so we would not have to eliminate it. Now let's move on and talk about something slightly different. So far, we've been looking at solutions to differential equations, but we haven't actually specified what allows you to determine precisely what the constant is. Remember that since you're dealing with derivatives of the equation you're trying to find, that you generally find families of solutions up to that constant plus c. How can you then pin down what plus c is? The general solution to a differential equation will ignore the initial conditions and leave it as plus c. That would be the general form of the solution. A solution for a particular problem, however, it has what's called a particular solution, which has to satisfy any initial conditions given, and it will specify the constant so that you will no longer have plus c, but as in previous equations, you'll have a definite constant, even if that constant is, of course, 0. Now, there are 3 different ways that we can classify our differential equations: by type, by order, and by linearity. When we talk about the type of a differential equation, and there's only one independent variable that the derivatives are taken with respect to, then we call this an ordinary differential equation, or an ODE. If you take differential equations later after Calculus 3, you'll begin with a course in ordinary differential equations. This is usually what students refer to as Diffie 1, which is the first course in differential equations. Then there is another type of differential equation. Since in Calculus 3, you will have to start to shift to the three-dimensional world that we live in, your independent variable will no longer be just x, but you will have x, y, and z, and occasionally we're going to throw in time as well. Of course, you can extrapolate, and you could have as many independent variables as you choose. In the Calculus 3, we typically deal with 3 or 4, x, y, z, and possibly time as well. In that case, when you do a derivative, or an integral for that matter, you have to specify which variable, which independent variable you're doing it with respect to. In this case, it's called, instead of just a derivative, a partial derivative. Or when you're looking at the integral, you'll use the differential that specifies which variable you're doing it with respect to. In this case, if you have an equation that has derivatives in it with respect to two or more independent variables, in other words, you have a derivative with respect to x and a derivative with respect to, say, y in the same differential equation, then we would call that a partial differential equation, or a PDE. This is what most students refer to as Differential Equations 2, the second one-semester course in differential equations. So we start with ordinary differential equations, and we very rarely look at partial differential equations in the first semester. The second semester, however, we focus largely on partial differential equations, since of course we do again live in a three-dimensional world. We're going to stick primarily with ordinary differential equations because we're still in Calculus 2. It's not until Calculus 3 that you introduce more than just one independent variable at a time. The second way that you can classify differential equations is by what's called the order. Now, the order of a differential equation just refers to the highest derivative in that equation. So in the two examples we've done so far, we've looked at differential equations that had both y prime and y double prime, or the first derivative and the second derivative. Just like when you call a polynomial degree 2 or degree 3, depending on the highest power on the variable x, you'll call a differential equation degree or order 1 or order 2 if it has the first derivative as the highest derivative or the second derivative as the highest derivative. The examples we've done so far are order 2 because they have the second derivative as the highest derivative of y in the equation. Linearity is a more difficult concept for most students to understand because students tend to think of linearity as, of course, lines, since that's what the first four letters spell out. And it is, in a sense, related to a line, and that lines do represent linear equations. However, linear to a mathematician does not just mean line. There's another meaning to the word linear. When we talk about an equation, in this case a differential equation, and we say that it is linear in the variables x, y, y prime, y double prime, all the way up to whatever your highest derivative is in the equation, we say that it is linear if we do not multiply any of these together, nor compose any of these with one another, nor raise them to any power other than 1. If it's not linear, of course, it's nonlinear. The best way to figure out what is and what is not linear is to look at an example. So let's take a look at some. In example 4, we want to look and determine the order, but we'll also talk about linearity just to help you get a feel for what it means to be linear and what it means not to be linear. Let's look at number 1 first off. The order again refers to the highest derivative of y that is in the equation. Since the highest derivative of y here is y to the first, This one, of course, is a first order differential equation. It is an ordinary differential equation. Is it linear? It is not linear. It is nonlinear. Why is it nonlinear? Well, because you have y and it's being squared. Remember that in the equation of a line, you have x and y, and they're both raised to the first power. They're not multiplied by each other, and they're not composed with each other. That's sort of what we mean when we talk about linear in mathematics. Let's now look at this one here. This one has, again, the first derivative. Yes, the first derivative is being squared here, but it's still the first derivative. So the order of this one is, again, first order, and it is also nonlinear. Cannot raise y, y prime, y double prime, or any of the derivatives of y to any power other than 1. X you can, but y you cannot. If you raise y or any of its derivatives to any power other than 1, multiply them by each other or compose them with each other, then it fails to be linear in y or its derivatives. Let's now look at the next equation. In problem number 3, we have y triple prime, which means the third derivative. We also have y double prime and y prime. Note that y double prime and y prime are multiplied together. Because they're multiplied together, that means that it fails to be linear. It is, however, third order. Sorry about that. So this becomes third order nonlinear. In the next equation, you'll see that we have a t squared. T is often used for the independent variable in differential equations because you can parameterize the solutions. And since t is often used for parametric equations, then t is commonly used as the independent variable in a differential equation. Now this one has y prime and y double prime. It does not have any higher derivative, therefore it must be second order. It is also, in fact, linear because it does not have a higher power on y, y prime, or y double prime. They're not multiplied together, and they're not composed with each other, so it is linear. Let's look at the ones on the right. Note that we have dy dt written here. Remember, this is just a different notation, and you could, of course, replace this with y prime equal t. This one is first order, and it is linear. We do not again have y prime multiplied by any of the other derivatives of y, including y itself. They're not composed. What about problem number 6? If you want to write it in the prime notation, you could write y prime plus y double prime equals 3x to the fourth. This would be a second order ordinary differential equation, and it is linear. What about the last one? This is y double prime, that is actually y prime, but being squared, plus 8 times y prime plus 3y equals 4t. It is fine to multiply the first derivative by any constant. You simply cannot multiply it by any of the derivatives of y, including the 0th derivative, which is y itself. You also cannot raise those to any power other than 1. Because we have y prime being squared, it will fail to be linear. It is a first order ordinary differential equation, but it is nonlinear. You'll notice I have no examples here for what a partial differential equation looks like, partly because you haven't learned them yet, and you won't until Calculus 3. I will write one down for you though, because they're very easy to spot because they have a different notation. Let's write one down. In this particular equation, you can see that it is very different from what we typically see for the derivative notation. You have a different symbol here. This symbol is used for partial derivatives, meaning that you have more than one independent variable. How can you tell the difference between the independent variables and the dependent variables? Well, the notation gives it away. Again, the genius of Gottfried Leibniz is simply astounding. When you look in what would be considered the denominator of the notation, that indicates that x is an independent variable. That means that t is also an independent variable. And since y appears in what would be considered the numerator of the notation, y is a dependent variable, but it depends on both x and t. Because I have two different partial derivatives in this equation, this is considered a partial differential equation, or a PDE. In this particular one, because I have the second derivative, it would be order 2. Because I don't have any of the derivatives raised to a power other than 1, and because none of the derivatives, partial derivatives in this case, are multiplied together or composed, then it is in fact linear. Let's talk about what we typically use differential equations for. Differential equations is one of the most highly used areas of mathematics in the real world, because in the real world we have problems we're trying to solve. We're trying to work out how COVID-19 is spreading. We're trying to predict when it's going to peak. We're trying to predict how many people might get sick, how many people might die. We're trying to predict when all kinds of things happen. And because we're doing that, and because we do know something about the situation, as in how many people were sick at a particular time, those are called initial values. And when we take the differential equation together with one or more of its initial values, we can call that an initial value problem. In general, you'll need the same number of initial values as you have the order of the differential equation in order to come up with a particular solution. Remember, the difference between the general solution and the particular solution is the general solution gives you a family of solutions up to the constant plus c. However, when you're looking at an initial value problem, if you have the same number or more initial values than you have the order of the differential equation, you should be able to pin down precisely the value of your constants so that you would get a particular solution for that situation. Now, when you have a situation and you're trying to find the general family of solutions, the general procedure is to take the antiderivative of both sides of the differential equation. What do you do first? Well, first you solve for the highest order derivative. You isolate it on one side of the equation. Then you take the antiderivative of both sides. Taking the antiderivative, of course, means that you're taking the indefinite integral. And because you do an indefinite integral, you must get a plus c. Then you could use that order of derivatives initial condition, if you have it, to find the value of c. You'll repeat this process, isolating the highest order of the derivative present in the equation at that time, until you have no derivatives left. And hopefully at that point, you'll know what the general solution is. Let's look at example 5 and try to apply the steps we just talked about to finding the general solution to this differential equation here. Now, I will warn you that this is very unusual. Typically, when we have a differential equation, we have more than just y prime. We typically have y prime, maybe y double prime. It's usually not this simple. In a differential equations class, you cannot expect to see things like this, except possibly on day 1. To begin, what we want to do, of course, is isolate whatever is the highest order of the derivative that we have in the equation at that moment. We only have y prime, and it's already isolated, so we're good to go. In order to complete this, what we want to do is take the antiderivative of both sides of the equation. Now, when we do this, we are technically taking the derivative of both sides of the equation with respect to the independent variable, which is, of course, dx. Now, we'll need to talk a little bit about how we can do the antiderivative of the left side of the equation, given that this is y prime. Now, Remember that we can rewrite y prime in a different format. Again, this is the genius of Leibniz's notation. Remember that y prime can be written as dy dx. Because we can write it that way, we can abuse the notation dy dx multiplied by the differential dx, and we can then write it as dy. Now, this is, of course, an abuse of notation, but why do we do it? Because it works. So what we'll do then is we will be integrating y prime dy after we've done it. Now, we're not really integrating y prime because remember what I did was I replaced y prime here with dy dx. And when I did this, I got this sort of cancellation. Of course, it's not really a cancellation because that's not really a fraction. This is notation. But again, it works. Notice that all that is really left is dy. So I get on the left-hand side just the integral of the differential dy. In other words, I've isolated the dy. On the right side, I have an integral of the natural log of x plus the tangent of x with respect to x. Now, on the right or left side, it's a simple matter now to integrate this, since the only thing I have in the integrand is the unwritten constant 1. That will give me y up to some constant, which I'll call c1. On the right side, I need to do the derivative of these two terms. To do the, or not derivative, the integral. The integral of natural log of x, of course, you'll have to compute using integration by parts. To integrate tangent of x, you'll need to write it as sine divided by cosine and use a u substitution. Pause the video here, do the indefinite integral on the right-hand side, then turn the video back on to compare your answer to mine. Maybe you've forgotten how to do the integral of natural log of x, but you will need integration by parts. Let's go through it briefly. You may want to have your finger near the pause button in case you need to stop me and check your answer with mine. In this particular case, we had done the integration on both sides of the equation, leading to y plus some constant c1 equal to the integral of natural log of x with respect to x plus the integral of tangent. Tangent I rewrote as sine divided by cosine. You'll see that I've color-coded the right-hand side so that you can follow each path without getting confused as to which part belongs to which part. I left off the y plus c1 on the left, although it is following all the way down. You'll see in green here that I have done integration by parts by allowing u to be the natural log of x and dv to be dx. Then you compute du and v by taking the derivative of u and integrating dv. When you are done, you need to use integration by parts, and the formula for it I've rewritten here in the center for your ease. When you're done with that, you'll end up with x natural log of x minus the integral of dx, which of course is just x again, plus some other constant that comes from that particular indefinite integral. To compute the indefinite integral of tangent, I wrote it as sine divided by cosine so that I could do u substitution by choosing u to be cosine of x. That gives you du is negative sine of x dx, and solving for dx, I get negative du over sine of x. Substituting those into the original indefinite integral leads to the following new indefinite integral in terms of u. Negative integral of du over u. When you're done, that becomes negative the natural log of the absolute value of u plus its own constant of integration, which I called c3. When I'm done then, I have y plus its constant equal to x natural log of x minus x plus its constant minus the natural log of the absolute value of cosine plus its constant. Let's solve this for y. When you're able to solve for the actual value of y, you're getting what we call an explicit solution, just like you did explicit differentiation and implicit differentiation. There are occasions where it's not possible to explicitly solve for y, But what you get instead is an implicit solution with y involved and possibly derivatives as well. By moving all the constants to one side and grouping them together, since a constant plus a constant minus a constant is still, well, a constant, we just roll them all together and slap one great big plus c at the end. What typically happens is that mathematicians and students do not track the individual constants all the way down. Instead, they wait to the very end and they add the plus c at the end. However, it is truly important that you not leave off the plus c. The general solution is a family of curves that will solve the differential equation, but there are infinitely many possibilities. The plus c is a huge part of the solution, and if you leave it off, you're going to lose major points. Let's move now to example 6, where we're looking for the particular solution to an initial value problem. We often will abbreviate that with IVP. Again, mathematicians, we like abbreviations for anything we have to write a lot. And let's face it, initial value problem is a lot of letters, and IVP is only 3. Here is our differential equation, y prime equals 4x squared. Our initial value is not necessarily when the independent variable is 0, though that's often the case. In this particular case, we're given a point. When you're thinking about a solution, you need to be careful and also consider the interval of validity or interval of definition or domain of the solution, if you will. If you have an initial value and your solution is broken up on the real number line into different intervals, you will need to pick the interval that includes your initial value. So let's take a look at how to solve this one. Again, we follow our general pattern of, if I can, isolate the highest order and take the antiderivative of both sides, meaning take the indefinite integral with respect to x. What this does is the following. I will now take this and I will integrate both sides. I'll have the integral of y prime with respect to dx and the integral of 4x squared with respect to dx. I'll rewrite the y prime notation as dy over dx times dx and abuse the notation on the left to get rid of the differential dx, which just leaves me with the integral of dy. At some point, you'll drop the interim steps and go straight to here. But it is important that you understand that this is actually what you're doing, and this notation abuse is why it's possible to do that. Now I can integrate both sides. Since this is such a short problem, I won't make you pause the video. On the left, I get y. Yes, there's also a constant of integration here, but I'm going to roll it together with this, guys, and slap one big plus c on the right. On the right-hand side, when I do the antiderivative, I get 4x cubed over 3 plus a constant. This constant is the combination of the constant from the integral on the right minus the constant of integration from the left. This is my general solution that you see here. This is the one that has plus c in it. Now, how do I get my particular solution to the situation I have where it must go through -3, -30? Now, if I look at this general solution and I look at the original problem, there are really no restrictions on the domain x. So it could be that this one would be defined over the entire real numbers. Let's now plug in our initial value, -3, -30, into the equation so that we can pin down what the value of c is going to be. This tells me that since y is -30, when x is -3, that I can replace or substitute -3 for x. That will let me pin down precisely what c becomes. This lets me then write that -30 is equal to 4/3 times a -27 plus c. Since the -27 divided by 3 would lead to -9, this tells me that -30 has to be equal to negative 36 plus c. Adding the 36 to both sides leads to the conclusion that c must be 6. Now I can rewrite my general solution to get the particular solution to this problem, which is that y is equal to 4/3 x cubed plus 6. That is our particular solution to that initial value problem. Now, we often know the form of the general solution, and we just want to find the particular solution. In a differential equations class, you'll go through how you know what the form of the general solution is, but that is really beyond what we're going to do here in Calculus 2. In Calculus 2, you'll be given the form of the general solution, but without an explanation of how you know it's the general solution. You'll have to wait for that for your semesters in differential equations. Example 7 is an example of that kind of problem. We're asked to find the particular solution to the differential equation y prime equal to 3 times x squared times y that passes through the point 0, 12, given that y equal to some unknown constant times the exponential number, Euler's number, e raised to the x cubed power. That is your general solution. So again, we're not going to explain how they know that this is the general solution. We're simply going to take it and take the initial value and try to find the particular solution to that differential equation. We'll go ahead and prove that in fact this general solution does solve it, but normally you would not need to do that. You can just take it on faith that it does. In order to prove it though, we need to compute y prime. This would give me, again, c as the constant coefficient doesn't affect it, but this would give me the exponential e to the x cubed power times the derivative of the power, which of course would be 3x squared. Normally, we would write this as 3c x squared e to the x cubed. That would be the value of y prime. Now plug it into the differential equation to see if it does in fact solve it. So what we're trying to determine is, does 3c x squared e to the x cubed truly equal 3 times x squared times the original equation y, which was c e to the x cubed? Well, a simple manipulation of the order in which we wrote the factors reveals that, yes, of course, they are equivalent. That means it is a solution to that equation. In order to find our particular solution, all we need to do then is plug in our particular point into the general form of the solution. We're told that the point 0, 12 is on the general solution. That means that when y is replaced inside with x being 0, we should end up with 12. That means that 12 has to be equal to c e to the 0 cubed power. Since 0 cubed is still 0 and e to the 0 is 1, then we know that the constant must be 12. Then we can write our particular solution as y, a function of x, equal to 12e to the x cubed power. Let's look at one more example before we end this video. In our last example, number 8, we want to solve the initial value problem y prime of t equal to 2t, and we're given the initial condition that when x is 0, y equals a negative 1. In order to solve this, first we want to isolate the highest derivative if that's possible. In this case, it's already isolated on the left side. So we'll simply integrate the two sides with respect to x. Well, now wait a minute. This is not x, this is t, which means that my independent variable must be t. So I'll need to change the differential that I'm integrating with respect to t. On the right, this gives me the integral of 2t dt. I can apply that trick of notation on the left-hand side to rewrite this indefinite integral as the integral of dy. On the right, if I integrate 2t with respect to t, then I get 2t squared over 2 plus a constant. The left-hand side, of course, just gives me y plus its constant, which I'll roll together with this constant. And yes, it is just fine to keep calling them all c, even though they may not be the same c. And this would give me, finally, t squared plus c. Now I take my initial condition that when t is 0, the y value will be -1. That means that -1 should be equal to 0 squared plus c, which means that my constant must be -1. Therefore, my particular solution is y as a function of t is t squared minus 1. I hope that you've enjoyed learning a little bit about ordinary differential equations. In the next video, we'll look at another technique that allows us to solve many ordinary differential equations, though certainly not all. This is the end of this video.